Start.
Somebody is a ninja.
Good afternoon, everyone.
Good
Good
afternoon.
afternoon, sir.
Good
Good
afternoon.
afternoon, sir.
Okay, thank you.
Good afternoon, sir. Good afternoon,
So I will commence the class now. However, the YouTube link have been shared with the subdates because the maximum the Zoom can take is just 300. So I'm on 291 now, 292. So once it's filled up, others will join via the YouTube channel. Okay, so please try to mute yourselves. It's now 300, so the rest will move to. So please do not omit yourself until you are asked to do so. Another thing I will do is to have a recording of the class. Then I will share it with the sub-dean to also share with the class as well. So please mute yourselves. Mute yourselves, please. So I've commenced the recording. I'm going to share my screen now and we'll commence the class. So this afternoon, what we'll be treating is not something that is strange to all of us. And if you continue to make noise, I will continue with the class. And I've asked you to mute yourself until you are asked to unmute. But some of you are so naughty that you are still making noise. I don't know what your problem is. I said mute yourselves. So now, what we'll be treating today is basically on gravity. And when we discuss about gravity, gravity is gravitational pull on objects on the Earth's surface. We all know we've been discussing about acceleration due to gravity, which we refer to as G. And that G, we all know, spans through the entire universe, and it varies from location to location. Now, we all know that, for example, if you have anyone standing on the weighing scale, what the person is measuring is the mass, not his or her weight. So a wrong usage, I want to check my weight. No, you are checking your mass. It is only when you multiply by G, that is when you call it your weight, which is in newtons. So the gravitational pull on the surface of the Earth is actually very, very important and very key, because that is what makes us to stand erect. That is what makes us to be able to do so many things on the surface of the Earth. However, if you go to the moon, you can't sit down peacefully because you'll be floating there as a result of a lesser value of G. That is what we have there. Now, due to what I mentioned earlier, the formula to calculate the force of gravity, which is the weight, is the mass multiplied by the G. And this is used to describe the weight of an object. So, and it's measured in newtons. So looking at this formula very closely, we will observe that the term weight is equal to, we can refer to it as the force of gravity. The term weight can be referred to as a force of gravity. Now, our planet Earth that exerts this gravitational strength G all around us and is measured in Newton per kilogram. That's the force acting on a unit mass. From here now, we can say our G will be equal to Fg divided by M. The unit of force is Newton and this is kilograms. And that is where we add this from. So the gravitational field strength of any location is defined as the force of gravity per unit mass. So some other objects such as us that is being pulled to the earth by its field strength. And that's why we can sit down peacefully, we can stand up peacefully, we can go about our daily activities peacefully. Now, the so-called G is always equal to 9.8 at or near the Earth's surface. Near the Earth's surface, on the Earth, the G is always 9.8, or which you can refer to this as meters per second square. But it is much weaker as you move away a significant distance from the surface of the Earth. As you move away from the surface of the Earth, it becomes weaker. And what does that imply? That implies that the G, as you are moving away from the surface of the Earth, the G reduces. And that's why by the time you are getting to the moon, it would have reduced and objects will be floating in the moon or other planets. Other objects in space, like the stars, planets, and moons, each have their own gravitational field strength, G. That may be stronger or weaker than that of the Earth, depending on their mass and the distance away from them. Depending on their mass and the distance away from there. Now, as a result of this now led us into the Newton's law of gravitation. For example, what Newton's law of gravitation is trying to explain to us is that it's trying to tell us that if you have objects on the surface of the Earth, or even any object with respect to the Earth, let's assume this is the sun, this is the moon. There is a force of interaction between these two objects, the sun and the moon. And that interaction is the gravitational force. Now, if the mass of the sun is ms, that of the moon is mm, and a distance of r between them, you can explain that force of interaction between them as given as this, where r, capital R, is the distance between the object and the mass of one of them, the product, and this. So we can see here that the gravitational field strength is always directly proportional to the product of the masses and inversely proportional to the square of the distance between them. And G is what we refer to as the gravitational constant. We refer to that as the gravitational constant, and this is the value of the gravitational constant. So the formula we have here allows us not only to determine the force of attraction between two objects, but also to calculate the weight on other planets or at altitudes above the Earth. Altitudes above the Earth. For example, if you are sitting down in the class, between you and others in the class, there's a force of gravity between you. And also the distance between you determines the force of gravity, gravitational field strength, because they are inversely proportional. As a result of the inverse proportionality, as the distance increases, the gravitational field strength between the two objects reduces. However, for the masses, as the mass increases, the gravitational field strength also increases. Any question? You can unmute yourself if you have questions. If you have questions, unmute yourself to talk. So that means I should assume no question. Now the next page. Determine the force of attraction between a 35 kilogram dog and a 7.6 kilogram cat watching each other from a distance of 4.8. Watching each other from a distance of 4.8. This implies that our R is equal to 4.8 meters and our masses 1, 2. So if you insert those values in G, so that will be G 6.67 times 10 raised to power minus 11. Minus 11 multiplied by 35 multiplied by 7.6 . So now, with this now, divided by the R, which is 4.8 square, you should have 7.7. It should result into this as the answer. That is what you will have there. Now, example 2. Find the weight of a 50 kilogram person on Earth using this. And how do you do that? To calculate the weight, mg, 50 times 9.8, that is almost 500 newtons. So find the same weight on Earth using this. You find the same weight on Earth using this. So what that happens is this. What is the mass of the Earth? Who is that? No, why are you raising up your hands?
Absolutely, sir.
Yes.
So I wanted to ask, are we to write our name in the chat box?
You don't need it. The Zoom is already taking the attendance. The Zoom is taking the attendance. And however, the Zoom cannot take all of you.
Thank you, sir.
So you don't need to do that.
Sir,
Yes.
gravitational constant always going to be given in the question if it's a different.
You mean in the exam?
Yes, yes.
Constants will be given during examination. They will be given. Constants will be provided in the questions. I hope it's clear. But however, if you solve as many problems as possible with it, you would have been used to the constant terms. It will be provided.
Sir,
Yes.
sir. So out of those that are using YouTube
And that was why I said
for,
the
for
attendance
attendance,
that was why I said the attendance is not necessary. Because there's no way they can write their attendance. Is that clear?
okay, sir. Excellent.
Because
Yes,
you are
sir.
adult. No need for attendance. This is an online class. I think you are not up to 300. The Zoom takes the attendance of those that attend. To take the attendance automatically. To take the attendance. So now for this, with respect to the Earth, that means the two masses we compare now is that of the person and that of the Earth, and the distance between them. So find the weight of this. We have done that. Find the same weight of this. Then find the weight of this person at an altitude of this. Now, so let's go. So this is the solution. Now, for a weight of 50 kilogram, you multiply with G, you have 490. Now, the same weight, you are being asked to find the same weight on Earth using this. So in order to find the same weight on Earth, this is the mass of the Earth and it is 50 here. So the distance between the object, because the object is on the surface of the Earth, it's lying on the surface. And when you look at that, this is about 6,400 kilometers. Then to meters, you have this. As the distance, if the object is here, distance between the center and where the object lies is our capital R. So putting in all the nearest parameter, you still have this. That's the same weight. Now you are asked to now find the weight of a person at an altitude of 170 kilometers. So that means it is 170 kilometers above the surface of the Earth. So you have this. Then you have so this is what you have here. So in order to get this, let's assume the 170 is this. So in order to get your R now, it will be R plus R. The radius of the Earth added to the altitude, the height with which it is to the surface of the Earth. So you find that, you insert it here, and finally you will have 465. You will have 465 newtons. Any questions so far with this question?
Yes, sir.
So what's the
Sir,
question?
if we add the distance between the objects above the Earth, will it all be in squared? The R plus R.
Yes, it's squared. That is why you have it here. Can you see it?
Yes, sir.
Squared.
Thank you,
Because
sir.
this is the formula. You have to still square it. So what you have
Good
here
afternoon,
is
sir.
R plus R. It's only when
Good
it's on
afternoon,
the
sir.
surface of the Earth, that is when you use capital R, single R. But when it's at an altitude above the surface of the Earth, you have to add that distance to it for you to calculate that.
Good afternoon, sir. So I have a
Good
question, sir.
afternoon. What's your
Sir,
question?
if they did not give us like the distance between the person and like the distance between the person and the mass, like the two mass, they did not give us the distance between the masses. Can we use like the radius of the Earth? Can we take it as distance of the distance of the person?
If they do not give you what?
If they did not give us the distance like between the two masses, sir,
Yes.
can we take the radius of the Earth like as their distance? Because we use it
No, you
as
can't
their
do that.
distance.
Oh. You can't do that. The distance between objects on the surface of the Earth must be given.
Okay, sir. Thank you, sir.
Okay.
Sir,
Yes.
good afternoon, sir. Sir,
Good
this
afternoon.
6.38 times 10 is about 6. Is that the radius of the Earth?
Yes, that's the radius of the Earth. It's
Okay,
only when
sir.
you
Thank you, sir.
approximate, that's when you approximate to 6,400 kilometers that we are used to.
Oh, okay, sir. Thank you, sir.
Yes. So, and that is what has been done here. You can see it has been added before inserting here.
I have a question, sir.
What's your question?
So how did you get the 5.8 times 10 raised to power 24 as the mass of Earth?
5.8 This,
5.98 times 10 raised to power 24, yeah.
this is the mass of the Earth.
Was it given in the question, sir?
It wasn't given, but in the question you'll be given.
Okay, sir.
But it's a constant term.
Okay, sir.
Israel Ajibade. Do you have question? Okay. Your answer down. So let us go back. Let us continue. Okay. Now consider the answers. Why is this weight less than at Earth's surface? You can see that the solutions we add at the Earth's surface, we add about 490. But at an altitude of 170 kilometers, it reduced. It reduced to 465. So why is this weight less than at Earth's surface? Because the gravitational field strength on the surface of the Earth is weaker as you move further away from its center. So as you are moving away from the Earth, the gravitational field strength reduces. That's why at that altitude, you add a lesser value. So now we can move on. So gravity in space. The space around a mass in which it exerts a gravitational influence is called its field. Now, your second semester, you still treat electric field, magnetic field, gravitational field. So the space around either an electric charge, a magnet, or gravity is what we refer to as field. In this space, for example, if you have a magnet here, north-south, so what is surrounding it? They are the fields and represented by the field lines. Represented by the field lines. So to find the gravitational field strength G at any location, combine both versions of Fg and this. Fg in terms of weight can give us this. Fg again can also give us this. So if you equate the two and find G, you will have this gravitational field strength. Make the small g the subject of the formula, you have that. So calculating the gravitational field strength, this is what you have as your G. So that is what you have there. So you are asked to find, okay, just like the example we treated. Here, M is the mass of the Earth, and R is the distance you are from the center of the mass. Note that capital R is radius of the Earth plus the altitude you are considering. Just like we solved that problem, plus the altitude you are considering. Now we have been asked to find G at an altitude of 100 kilometers. We all know that our G will be equal to what? Gm divided by R. So to get our R now, that will be radius of the Earth. That will be 6,400 plus 100 kilometers. Convert to meters. What do you have? 100
Sorry,
kilometers.
sir.
Yes.
Please, this place that you wrote G is equal to GM over R. Is it not supposed to be R square?
Is R square? Okay, R square. Yes. Sorry. r squared. Yeah. So 100 kilometers now, if you multiply by 1,000, 1, 2, 3, 4, 5. So you have the 100,000. So if you sum this up and you insert here, given the mass of the Earth, your G is also constant. You can calculate the G. So let's look at that. Let's see, to get the R, you sum it up. Your mg is equal to this. Cancel out the masses. You are left with this. So you have this. This is your G multiplied by the mass of the Earth, then multiplied by the distance. So finally, you have this as the solution. So I hope it is clear. So this was where we stopped. So we can then move on to the next one.
No, sir, it's not clear. Oh.
What is not clear there? What is not clear?
Clear.
Huh?
Talk now.
What is not clear? You are given this to calculate gravitational field strength, equating the what, this to this. Make G the square root of the formula. And the question was given to you. Find G at an altitude of 100 kilometers. So the first thing, determine your R, radius of Earth plus that kilometer. So now, if you do that, this M here will be the mass of the Earth, gravitational constant, and the addition of this, what you have here at that altitude, should give you your G. So is it clear now? Is it clear?
Yes, sir, it is clear. Yes, sir.
Okay. Okay. Now, let us move on. Another question. Determine the net force acting on planet B by the other two planets. By the other two planets. This is not too difficult. Planet B stays here. So if you calculate the interaction between A and B, the masses are given and the distance between them is given. So eventually you have something of this nature. So in order for you to be able to get the net force, this is going to be the net force. This is the force AB, then force BC. So the net force. So you can then calculate the net force. So in order to do this one now, what we need to do now is to find the FGAB, that will be the G multiplied by the masses. Then we have so you then have this divided by 3.6. Everything squared. You move on to the other one. So from here, to find this, that will be the G. Then you have the masses, 5 times 10 to the power 24, then 9.2. So now divided by the R. So now if you square this, you find that. So let's now go to see what happened. So this is it. Like I said, for AB, BC. So when you now have that, you then find the net force. This is it. That is it. So in order to determine the net force, so using the Pythagoras theorem, you can determine that. Arctan, since you know this, you know this. So I hope it is clear. Any question? Any question?
Sir, I don't. Where are we going to use the arctan in the question? Thank you, sir.
The arctan will be used when you are trying to calculate the angle between them. If you determine you have this FAB, FBC. So if you, the resultant is going to be this. Is that clear? But however, if we extend this, we extend that to that side. So the resultant here, you can always bring it here.
Yes, sir.
So that if this is FBC and you take decision to find this Y, which is the resultant, so you have to use Pythagoras theorem. Y squared is equal to FBC squared plus this. So that is basically what you will do. So from there to find the theta, the angle subtended,
Okay,
that will
sir.
be tan theta is equal to that. So finding the arctan gives you the value of the triangle.
Thank you,
The
sir.
value of the theta. Sorry.
I have a question, sir.
What's your question?
So, in the case of large masses like big buildings or big um, objects, are we supposed to also consider the distance between one side and their center of gravity, like the middle and the side? Are we supposed to consider that distance too?
That if you have a large object, okay, you
Yes,
mean considering the center of gravity. If it's a
yes,
question on center of gravity, that will be given to you separately. But this is
okay.
just on gravity generally.
Thank you, sir.
Okay. So any other question? So the absence of questions, let me continue. Now we then move on to example 5. So you have this.
Excuse
So
me,
by
sir,
the
please, I
time we
have a
look at the
question.
example 5, it's just trying to let us understand the relationship between F now. The above is now changed as follows. The diagram you have here, you want to change it. So each time you change, you find the new gravitational force, which is G. So now what you have here now, there's a distance between the two objects, and the FG calculated is this. Now find the new gravitational field if M is tripled. If the small m is tripled, this one, what happened to the F? Can you talk or mute yourself? If the small m is tripled, what happened to F?
It will increase.
F become bigger.
It will increase also by 3. Why?
Tripled
Because
because it's
they are
directly
directly proportional.
proportional to the mass.
Direct proportional. Thank you. Now the second one, M, the capital M is tripled and M is reduced by half. Capital M is tripled and this is reduced by half. These are some scenarios that you can have, and all this is to test your knowledge, your understanding of the concept. So this is that. We have done this. Okay. So F is directly proportional to M. So the F and the nu. This is what we have. Now, why we have this one now? For the F old, that will be G. For the F new, it will be tripled. So that will be G 3m m over r squared. Now, if you are comparing the two, you will observe that these are constant terms. So F new divided by F old. So you can then have, if you compare these two, you have F new is equal to F old so when you do that now, derivatives will be F new divided by F old, which will then be equal to because what you have here now, you still have a replica of F new divided by F old. So you use this to divide this. But you then see that if you do that, this new here, the M here is dividing the old one here. because it will just be a matter of the G will cross out. That will be 3 mm over what? Over mm. So we'll still observe that the old mass is coming down, while the new mass is above. And that is what has been done here. So finally, your new F will be 1.2 times 10 to the power 22. Any question? Yes? I can't hear you. I can't hear you.
The respect of F without like a figure. Can we just say that the mass is that the mass is 1.5 I don't have to it is reduced
In fact, I can't hear you. Your network is poor.
Excuse me, sir. This 4.1 times 10 raised power 21. Were we giving the question?
The 4.1.
Yes, times 10 raised power 21 that were taken as the F new.
Yes.
Okay. Okay.
You were given this. That's the old gravitational field strength for the two objects. Distance between them is this. We're given.
Excuse me, sir.
Yes.
Yes, sir. If we have two bodies that are equal in mass, will there be gravitational forces between them?
Yes, there will still be gravitational forces between them. Even twins or triplets in their mother's womb, there's gravitational field strength among them or between them.
Okay,
Excuse me,
sir.
sir.
But
Sir, please, can you explain why you are dividing the new M over the old one, sir?
Yes, because it is a ratio. Because this is the new one that we want to find.
For them things.
And the new
Okay,
one
sir.
you are finding will be a function of the old one. I hope it is clear.
Yes,
The
sir.
new
Thank
one
you,
you
sir.
are finding, this was the old gravitational force we were given. So we are finding a new one. It has to be a function of the old.
Thank you, sir.
sir,
So for
about my
example now,
question.
like
Okay.
the simple mathematics that we know from primary school, when they say Peter is 3 years old now, while John is X years old now. In 3 years' time, Peter's age is twice that of John. So find the age of X. You can see that the new one will be dependent on the old one. I hope it is clear.
Yes, sir.
Okay.
Thank you, sir.
Excuse me, sir.
Yes.
Okay, sir. What you are doing now, you are comparing that relationship, that direct relationship between the force and the
Yes.
M.
This is what I've done. This is the old one. This is the new one. If you find the ratio of these to this, eventually this will cross, and that is what I've done here. The G is constant. So this over this. Also, the R square will also go off because they are the same. Distance between them are the same. To go off. So what you are left with are just the masses that you see here. Why the new one has 3? Because it's tripled, multiplying the smaller mass. So that is what you have here. I hope it is clear. So the F old, if it's cross multiply, it goes to miss the whole of this. And that is what has been done here. Is it clear?
Excuse me, sir.
Yes.
So, if the two equal masses are exerting gravity, which one will be pulling which one?
It's just an interaction between them. None will be pulling. But you can calculate the gravitational free strength because
Yes.
the gravitational effect of the Earth is acting on both. If it's acting on both, then between them, what is existing?
Okay.
Is that
But
clear?
but what if they are in space with no larger bodies nearby them?
If they are in space, even if you go to space, you still find objects living there. There's no space. Those that have gone to space, you'll find objects living there.
Okay, so
So there'll still be some form of interaction, except you are in a closed system, isolated system, where you do not have interaction with your environment.
Okay. Thank you, sir.
Okay. So the next one, we are asked to find the capital M. Okay, find the gravitational force if M is tripled and M is reduced by half. This is in two phases now. Can you see? So it's now about these two now. So the effort will still come here, M nu over this, M nu over this, the smaller one. So once you do that, you still have this. So the next question, if M is 1/10 as large, if M is 1/10 as large, why your, let's see the question. M is 1/10 and R is triple, that's the distance. That's where you now find R surfacing.
Excuse me, sir.
Yes.
Sorry, I'd like to ask something. In the question you just did before we move into this 1 over r squared, I'm seeing that
Yes.
the second question said that m to the small m was halved. But in that equation, I'm seeing 5. I'm just a little confused
You are not
because
seeing 5, it's
the
0.5.
m is 0.5. Sorry, I'm seeing 5.
0.5.
Sorry. Thank you, Michael.
Okay.
Thank you, sir. Thank you. Sorry,
Okay, my
my
pleasure.
mistake has been there.
No problem. So you can see what this is 1/10, that's 0.1, and this was tripled. So the old over the new. Why do we have old over new for the distance between them?
Because
Why
say
is
if
it
the
not
old one
new
will use
against
and
the
get the
old?
new one.
Because of
Because
what?
it is an inverse, sir.
It is an inverse. They are inversely proportional. So take note of that. I hope it's clear. So that's the way you go through the questions if given. And this is the last one. This is the last one. So given all the necessary parameters, you should find a new one. What is here is M is quadrupled and R is increased to this. M is quadrupled and R is increased to that. So all those things have been found, and this is what you have. Quadrupled, you have this. R is what? R changed. Yes. Initially, distance between them was this. So the R changed. So old against new. So you will have this. That's the new force between them. So any question? So in the absence of question, let's go back.
So for that 1/10, I don't understand.
If you say 1/10, change this to decimal. What do you have?
Yes, sir. We are
1/10. That gives you what in decimal?
yes, sir, but sir, you said 1/10 as large. I'm not supposed to find the 1/10 value of m, then add it to the original value of m.
Yes, that was what was done.
Yes, sir,
It
no,
means
but
the new one was 1/10 as large.
as the old, I'm not supposed to add the 1/10 value of m with the old value of m.
No. It's a matter. This is a matter of English. Let's go back. Okay, M is 1/10 as large, and R is tripled. M is 1/10 as large. Can you see? The new, the old. If it says 1/10 as large, it's just semantic, it's English. It's not that you are supposed to add, no.
Okay, sir. Then for the C, we did old. Okay, sir. Old over. Okay,
For
sir.
the what?
No, sir. I understand. I understand, sir.
For the
Why
R.
are we?
For the
Yes.
R
Why
is
is it
opposite
old
because it's
over new?
inverse.
Then for M is new over old. I
This is
understand for
directly
M.
proportional from the equation. Can you
I
see
know.
it here?
Yes, sir.
That's the reason.
Okay.
Yes, sir. Yes.
I hope those on YouTube are learning from the questions as well. It's a pity we can't go beyond 300. So let's continue. You have started making noise. Now we then move on to the Kepler's 3 laws. The Kepler's 3 laws are: 1, that the planetary orbits are elliptical with the sun at one focus. So the sun stays at one focus, the earth moves around the sun, likewise the moon. And when they move in an elliptical what? Elliptical orbit. And that's what you see here. Note that many orbits are very nearly circular. For such cases, we can state them as being circular in nature. So if they are circular, that means we can treat them as centripetal force. But usually they are elliptical, but we can take them assumption that they are circular. So therefore, we can infer from that centripetal force exists when they move around. And it is as a result of this moving around that results into the day and night, as well as the variation in the seasons that we have, except now that we don't know what God is giving us, or maybe it's due to climate change. We can't even determine that. But we now find that the rain is falling when it is not supposed to fall. That is God working. Now, the second law states that a line joining the center of any planet with the sun traces out equal areas in equal times. A line joining the center of any planet with the sun. This is the center of the earth. And you have center of the earth to the center of the sun. As the earth rotates round the sun, it's cutting out equal what? Equal radius. That is what the second law is saying. The first law says that you have many orbits moving around in a circular manner. And the second one says that the movement round traces equal areas in equal time. So this statement tells us that for every elliptical path, a planet travels at greatest speed closest to the sun, where G is the greatest, and travels slow west at its farthest point from the sun. So the gravitational effect on those planets are how far they are from the sun. And that is what gives them the movement. And the last one, if R is the average orbital radius, like I said, you have the Earth, you have the sun. This is the R. It's cutting out equal area at equal time. So if that is the orbital radius and T is the period, Since there's a movement round, so you can always calculate the period. And that's why you see the Earth, you have its revolution, it revolves. At the same time, it rotates. It rotates about its axis. At the same time, it revolves. When it revolves, that takes in 365 days or 366 in a leap year. So the R we have here, that is the average orbital radius, this one. And T is the period, orbital period. So the ratio of these two, it's a constant. The ratio of the average orbital radius to the square of the orbital period, it's always a constant term. It's always a constant term. So these are the three laws of Kepler's. Those are the three laws of Kepler's. Now, and Kepler's law came into being because the Newton's law couldn't explain certain information. So when you go through this now, we can then derive the Kepler's third law from the Newton's second law and find a way to get the Kepler's constant. Because we have said is a constant, the ratio. Start by examining a satellite of mass m traveling in a stable orbit with a period of revolution of this around the central planetary mass. So which means the small m and the capital M, they are interacting. So the capital M, that's the planet. The satellite is M in a stable orbit round. So if you assume that this is the Newton's gravitational concept here. However, for the centripetal force, that will be equal to mv squared over what? Over r. But what is your v? Your v is omega r. And how do you get omega r? Your omega is what? That's the angular velocity. So what is angular velocity in terms of angular velocity is what? 2 pi over what?
2 pi over t.
2 pi over
Angular
t.
velocity is 2 pi over t.
So if you now substitute this into mv squared over r, it gives you this. Because the r is you are dividing it so it goes up while the rest comes down. Now, if you have the gravitational force and the movement around the satellite around the planet, if you equate these two, you have this. If you equate the two, hence this m cancels this m. The r cancels one r. Or you can cross multiply if you wish to. So if we cross multiply here, since no, let me. If you cross multiply, that means you have r cubed 4 pi square to be equal to g m t square. Now, with respect to the Kepler's third rule, we have r cubed. We have r cubed divided by t square. Then we are left with gm divided by 4 pi square. So the whole of these are all constant terms. So we take this as our k. So if that is the k, we can find the Kepler's constant. We can find the Kepler's constant. we can find the Kepler's constant between the satellite and the surface of the Earth. So I hope it is clear.
Yes, sir.
Okay. So now we have a question here. Question 7.
I have a question, sir.
Now, what's your question?
I just wanted to confirm if that pi was 180 or 22/7.
It's
Like
22/7. It's
22
22/7.
Thank you, sir.
The pi there is 22/7. Because the elliptical orbit is taken as a circular orbit. So that's it. Now, since we have been able to find that this is the ratio and K is the Kepler's constant. So from here, R cubed will be equal to this. So if we have two conditions, just like your Boyle's law and your Charles law. Under your Charles law, what do you have? V1 over what? T1 is equal to V2 over T2. So you can bring your V2 here. You can rewrite it as what? V1 over T2 be equal to T1 over what? So that is what has been done here for two conditions. To solve ratios. Now let us look at one of the problems under this. That's question 7 before we move on to the next discourse. Now we have that a telecom satellite orbits the Earth once every 24 hours, and that is what we refer to as geosynchronous orbit. So what is the altitude of these satellites? What is the altitude? So the first thing we need to do, if it orbits around, that means we have the period. And how do we define period? That is number of a cycle in 1 second. In 1 second. So that is what is called the period. We now know that in 24 hours, so if you convert that to seconds, you have this. And earlier we knew that FC can be equated to FG. What we did earlier. From here, you can get your R cube. That's the distance from the Earth to the satellite. This is the Earth, and the satellite is here. I hope it is clear. So from here, if you find that distance R is the entirety of this. So to get our R, we have this. This is the value of our R. But in order to know the distance of the satellite from the Earth, that means we must subtract the radius of the Earth from the entire R. And that is what has been done here. This is what you have. I hope it is clear. Do you understand that?
Sorry, sir.
Okay.
Sir, which mass do you use? Which mass do you use in the formula?
That's the mass of the Earth. This is it. It's the mass of the Earth. Is that clear? That of the satellite has crossed out. Did you see it here? It has crossed out. So you are left with the mass of the Earth. So when you now get the entire distance from here to here, the altitude and the radius of the Earth, that's the distance between the interaction. You then subtract the radius of the Earth from it to get the distance of the satellite from the Earth. Any question?
Yes, sir. Sir, what is the geosynchronous orbit that you mentioned?
Geosynchronous orbit, that is the orbit, the satellite rotating. We refer to it as a geosynchronous orbit because it's relatively to that of the Earth. It's rotating relative to the Earth. And it is rotation that leads to telecommunication, that leads to we using our DSTV, our StarTime, our GoTV. But it continues in that orbit until it expires.
Okay, sir.
Okay. So for question 8, Mercury's year, which is 88 Earth days and its distance from the sun. So you are talking about Mercury and sun now. Is 0.3 AU, angstrom. Now, in order to find the orbital radius of the Venus. Orbital radius of the Venus. So that is what we have been asked to find. Still using the same formula, rearrange to have this, which is your K. So you find K, this is the K that we want to find now. Since we know for Mercury, this is this over 88. For Venus, we don't know over this. So we can then equate the two and find R. We equate the two and we find our R. This is what we have. We equate the two, we can find our R, which will be equal to this. So that's what you have with that particular question. Let me see. I think we are almost rounding up. Now, we will discuss about, from here, gravitational potential. We also have electric potential, gravitational potential. When we are near the Earth's surface, we calculate this, the potential of an object, as the work done to lift the object to its new height. The work done to lift the object to its new height. Where this, because you are raising it to a specific height, that will be mgh, near the Earth's surface. So the value of h is measured relative to some point that is chosen by you. So for a pendulum bob, h is equal to 0 at the bottom of its swing. For an object that is dropped, h is equal to 0 where the object lands. So which means we are the ones that will choose the 0. Now, whenever an object is lifted, the potential energy is increased, resulting in a positive work done. Why is the potential energy increased? Because potential energy is dependent on the height. So the more the height, the higher the potential energy. If that object is lifted to infinity, then the potential energy will be 0. But there's no way you can go and measure the height if it's at infinity. So another way, when an object falls, the potential energy decreases because the height is decreasing. So since the potential energy decreases as the object falls from infinity to Earth, and since EP is equal to 0, then it then increasingly becomes what? A negative value. Becomes a negative value. Now, what we have here for gravitational potential, you can see the difference. Because of the gravitational potential, you'll be subtracting the initial from the final. And that is what led to this negative sign. But you can still remain, the masses still remain, but the R changes for gravitational potential. So for the gravitational potential now, or you call it EP, some text will say V, is equal to minus GMM divided by what? R. No R squared. No R squared, like we have for the force, that is R squared. And for the force, no minus sign. I hope it is clear.
So,
Yes.
the part of the negative value, like based on the knowledge I had of gravitational potential before, I didn't know that there was supposed to be a negative introduced. So that part is not really clear to me.
There will be negative because that is the work done against gravity in moving a mass from one location to another location. Gravity exists, you are trying to move against gravity. I hope it's clear, under potential, not under force. Because gravitational potential is the work done. It is the work done.
Okay, so thank you, sir.
Okay. It's just like under your heat. Under it, you have work done on and work done by the system. I hope you remember that. Work done on the system, work done by the system. So you are moving against gravity.
Hello, sir.
Yes.
Professor, so should the negative sign appear in our answer? Right.
The negative sign?
Yes, sir.
No.
Okay, sir.
Because potential energy cannot have a negative value.
Okay, sir. Thank you, sir.
So you are finding the potential energy for an object in space relative to central planetary mass. Also, potential at infinity is zero. Is zero. Even if it appears, it's only trying to tell you the direction of, even if it appears, it can appear, but it's only trying to tell you the direction. It's just like you have a force. If you have a minus sign for your force, it's only telling you it's to the opposite direction.
Okay, sir, so we'll not use the minus sign while calculating.
The minus sign. No, the minus sign will come out by itself.
We'll
Because
not
you are
use
moving
it
an object from infinity to a specific point.
So, sir, we'll not need to use in the calculation, like multiply the minus by the answer we get after calculating.
Multiplying what?
The minus by the answer we get after calculating.
Yes, whatever the answer you have, you can put the minus, you might not put the minus. But if you put it, is only trying, you are showing the correct physics, trying to let us know that the movement is against gravity.
So, but what if we get the minus answer? So do we do minus the minus answer multiplied by the minus to make it plus?
Yes, then it will change to plus if that is the case. But normally the minus sign comes out as a result of you subtracting. The final potential minus the initial potential, which is in relation to the distance.
Excuse me, sir. Sir,
Yes.
the EP final, sir. Sir, please, can you help me to explain why it is zero, sir?
The EP final, why is it? It is zero. EP final is zero because when it gets there, it will stop. It's just like you throwing an object up. Is that clear?
Yes, sir. Thank
If
you,
we
sir.
throw it up, you have potential energy, which is equal to mgh, isn't it? It gathers potential with respect to what? Height. At the maximum height, potential energy will be 0.
Okay, sir. Thank you, sir.
Is that clear? Because it would have reached its peak.
Yes, sir.
So I hope it is clear.
Sorry, sir.
Yes.
So why is the graph FG against R? Why is not FE against R?
Why is it not?
FE against R.
No. They are only showing a relationship between that of force and that of gravitational potential. So work done is area under the graph, under the force. Force is proportional to what? R square. Is that clear?
Yes, sir.
We also have similar thing under where, say, those of you that will still offer physics in the second semester, under electric charge, you meet that. We have electric force. We also have electric potential. Under electric force is proportional to R square. Y here is proportional to R. So I hope it is clear. So we can now see this. For this, this is this, this is this. So if we bring the two together, you can see the inertia has come to lead because of plus that will result here. I hope it is clear. So the potential for one as minus, the potential for the other one as minus, like the person asked the question. This is what you have. So energy added is positive energy. That's why you have this. So you then have an example on example 11. See. 11. Okay. Determine the work done to move a 3.5 times 10 raised to the power 4 kilogram cargo of space junk from an altitude of this above the moon surface to a radii of this. Work done in moving a cargo of space junk is in the space, but is a junk, maybe in the moon or other planets. So from an altitude of 430 kilometers above the moon surface. Now, what do you do? Just like it was stated earlier, gravitational potential, final minus what? The initial. So because of the plus here, the initial leads, and you subtract the final from it. So when you put in the necessary parameters, this is what you have for the masses and for the distances. This is what you have. Why did we sum up here? Why did we sum up? For the distance.
We're given altitude.
Yes, we are giving altitude, yes. So
Good afternoon, sir.
Good afternoon. How may I be of help to you? So now we have this. Because we are given altitude from an altitude of 430 kilometers. So that's why we have this here. You are adding this to this. And you have this.
So where do we get 1.74 times 10 power 6?
1.74 will be a parameter of one of the planets. Might be the radius of the moon. It's the radius of the moon.
Is it a constant, sir?
You are asking me, how about the radius of the earth? Is it a constant term? Is the radius of the earth changing? Oga? Is it changing? No. So that's that.
Sir,
Yes.
how do you get this 2.8 times 10 power 6?
How do I get?
2.8 times 10 power 6.
You were given in the question.
Sir, please let me see the question.
This
okay,
it.
okay. I've seen it. Thanks, sir.
Have you seen that? Yes.
Yes, sir. Thanks, sir.
So it goes in that manner. You solve. You insert the parameter. This is the correct physics.
I have a question, sir.
What's your question?
Is it not meant to be 1 over R2 minus 1 over R1?
1 over
R2 minus 1 over R1.
What is here? That was what I've been saying. Somebody mentioned it and we found it here. R2 minus 1, because it's a potential, it has negative sign. So this one has negative sign. So if you are subtracting them, this becomes plus. So the R1 will lead.
Yeah. Thank you, sir. I understand now, sir. Thank you, sir.
You can calculate that. Note that work done to lift an object is positive because EP, the gravitational potential is increased. That's why it's positive.
Excuse me, sir.
Yes.
So, is the mass of the moon given?
The mass of what?
Of the moon.
Yes, it's given. You have that of the mass. But these are constant terms that you yourself can search for on Google. You can check TikTok, you can check WhatsApp, you can check Facebook. So these are things you should be able to search for. Please.
Sorry, thank you, sir.
This person, let me see if I can mute that person. That person is disturbing us. Let me just mute all. Okay. Now, let us look at the next. Okay. I think it's about what we need to discuss. I think that's the last aspect of what we are to discuss. Conservation of energy in space. To calculate the total energy of a moving mass in space, we can state that the total energy is that of kinetic plus what? Potential. So if we now substitute, that of kinetic is always what? Half mv squared. That of potential is this. So if you have that now, so the parameters are stated here, where v is the speed of the object. Use total energy to find the unknown quantities of any mass. So what's the radius of the planet? We'll look at this later on. I want us to go through everything once and for all. So gravitational potential is here. Where R is this? But you can equate the two, the potential and the kinetic energy. Cancel spacecraft mass and solve for V. So At the planet's surface, you have this. Here, the speed of escaping object at the planet's surface must be great enough to provide kinetic energy needed. So here it's been equated. Gravitational potential is this. So radius of the planet is this. So we equate the gravitational potential to the kinetic, the two equated together. So determine the escape velocity of this. So all you need to do is to make V the subject of the formula. So let us look at question 12 and 13, and that is where we will stop for the day. Question 12 and 13. A 12,000 kilogram spacecraft is 7.2 meters from the center of a planet that has a mass of this. As it falls back to the planet's surface, the spaceship gains this of kinetic energy. What's the radius of the planet? So kinetic energy is given as this. So using conservation of energy, the total is that before, the total is equal to the potential energy. But as it starts to fall, total energy will be distributed to potential and kinetic. So for before now, that the potential is this. Substituting the parameters, yes.
Just plus all this kind of thing.
Eh?
Plus. New type of.
I don't know why these people will continue to disturb the peace of the class. So now from here, we calculate the potential to give us this. If we move further again, since we have said the potential we have here, you can see the minus sign still with it. Then the new potential plus the kinetic energy. So if you subtract, you have the new potential energy. So if you substitute in that new potential energy, you can calculate the radius through which it fell. That's the distance through which it fell. Any question?
Sir, please, can you quickly go over the explanation of the example again?
We all know that there's always conservation of energy, especially mechanical energy. The total energy of every system is equal to the kinetic energy added to what? The potential energy. Now, the potential energy was initially, before it starts to fall from the orbit, there was no kinetic energy. It had potential energy. And that's why we have this. But the moment it starts to fall, the total will be converted to both potential and kinetic energy. Now, as a result of this, we can then have a situation where we have the, now calculating for the first phase, the potential energy is given as this, with the minus sign, minus Gm1 M2 over R. Now, when you have this now, this will now be equal to the new potential and the kinetic energy. And you are given the kinetic energy in the question. 9 times 10 raised by 11. So from there, you can calculate the P nu. So the P nu, when you insert it here, you can get the distance of the satellite to the planet, which is R. And that's the solution. Which is R, which is the solution. I hope it is clear. Is it clear?
Yes, sir.
Okay. Because of time, there is also what we refer to as escape velocity. I don't need to go into the derivation. Escape velocity, for example, we are launching satellite into space, which means you must give it a velocity that will make it to go out of the radius of the Earth. So escape velocity is usually given as square root of what? 2gr. Square root of what? 2gr. G is the acceleration due to gravity or gravitational field strength. And r, that's the distance. So when given that, it escapes. Even when launching, aside from, yes, satellite goes with a rocket. They are attached to rocket. So the rocket is the one launched into space. And when launching, you give it a velocity that will make it to escape from the vicinity of the Earth. And that's why we refer to it as escape velocity, given as square root of 2gr. So any question?
I'm sorry, sir.
Yes.
So I want to know something about that energy, that conservation of energy that you mentioned. I want to, is it that if a question is given now, we are the one that will look at it? If this
You have to
energy,
look at it now. Did they mention here that you have to interpret the question?
No.
You can see using conservation of energy is not stated in the question. You are the one that will actually have to analyze the question.
Okay. So we are the one that will know the energy with the energy, the two energy involved.
One is given, it's here. This is it.
Okay.
That's the kinetic energy. It's given. So you need to calculate the new potential energy. And you can only derive that from the old. You cannot just jump to the new. You must come from old to new. And that is what we did here. Is it clear?
Yes, sir.
Okay. So any
Sir.
other question?
Yes, sir. I have a question, sir.
What's your question?
Sir, please, when are we going to get the slide, sir?
I will only share the recording. I will send it through the sub-beans. They will share it with you.
Thank you, sir.
Is that clear? The recordings of the class are there. I recorded it. So they will be shared with you.
Sir, one more question, sir. Sir,
Also, if you go to the YouTube channel, you should see the YouTube channels have been shared with the sub-bean. So you can also view through the YouTube channel.
Okay, sir. Sir, based on the physics assignment that we were giving earlier, sir, is it compulsory that we must write out the question before putting the answer? So we can just go straight to the answer, sir.
No, you can go straight to solve, writing the question number, 7 point this, 7 point this, 7 point this.
Okay, thank you, sir. God bless you, sir.
Okay. So for those that couldn't get the books are now available in the bookshop. Okay. So thank you. Do have a wonderful weekend ahead of you.
God
Thank
bless you,
for the
sir.
attention. Okay.
Thank you, sir. Right, sir.
Okay. My
Thank
pleasure.
you so much.
sir.
Thank
Okay.
you, sir.
My pleasure.
Thank you, sir.
Thank you, sir.